He has also served, just a second. He has also served as chairman of multiple technical committees within DRDO and contributes significantly as a reviewer for reputed journals, conferences, and PhD thesis in his area of expertise. He has also served as an expert member on various academic and technical interview boards. Dr. Sahu has been recognized with several awards, including the Best Industry Expert Award, Amity University 2018, and Lab Scientist of the Year Award, DRDO 2019, for outstanding scientific contributions. Beyond DRDO is currently an expert member of MIGHTY Interministerial Committee on Quantum Technologies. He also contributes as a distinguished expert with AICT for the review of Atal faculty developments and the Parak project. So we are grateful to him for accepting our invitation to be speaker in this FDP. Over to you, sir.
Thank you, Professor Mitharwal, for the nice introduction, and thank you for having me here on this event. So let me share my presentation. So is my presentation visible?
Yes, it's visible.
Yeah. So let's begin. So good afternoon, everyone. So today we will be covering quantum entanglement and how this quantum entanglement is realized by Bell states, and then we will try to understand and explain quantum teleportation. And parallelly, we will be doing experimental things on Qiskit and IBM Composer, how we can create Bell states or how we can do quantum teleportation implementation. So this will be typical flow of my talk today. So first we will be understanding quantum entanglement, and then we will explaining this quantum entanglement with help of Bell states. So then we will derive the general equations for Bell state creation, and then we will be having the circuit, and we will see the application of Bell states in various domains such as quantum teleportation, superdense coding, and many others. So let's begin. So maybe this quantum entanglement has been discussed in previous talk as well. So just we will be recapping that thing. So this entanglement is nothing but just the states which are in superposition are correlated. Means there are more than one state and they are correlated. They are correlated based on different parameters. So let's take an example of two qubit system. So where these two qubits are in superposition of each other, and when we create a entangled state out of those two qubits, then the measurement outcome of one qubit is always related to the other one. Or basically, these two states are correlated. We cannot define or describe them independently. We can define them as a combined system, cannot be defined as an individual qubits.
Can you do a slideshow full screen, because we are just seeing a summary of all the slides.
No, actually I have done already this thing. Just a second. So are you able to see the entanglement slide?
No, actually we are seeing the summary of slides. We are seeing all the slides. I mean, around
Okay,
15
then
slides.
let me share my entire screen. Then it will be a good way to share. So so now are you able to see my entire screen or the presentation?
Yes, now we can see one single slide.
Yeah, so that's it. Okay. So the flow will be talk of the flow of this talk will be like this. First, in this, we will try to cover entanglement, and then we will see that how we can create entangled state, which we call as a Bell state, and to have the circuit of the Bell states. So using quantum circuit, how we can generate Bell states, and there are different Bell states. There are four. So we will see how we can generate these four types of Bell states using quantum circuit, and then we will see the application. In the application, there are two major applications we will be covering in our talks. Those are quantum teleportation and superdense coding. And there are many other applications. If time permits, then we will cover them as well. So this entanglement is nothing but just the correlation the quantum system exhibit when there are two or more quantum mechanical systems and they are in superposition, and when they exhibit correlation, then we say that these two or more quantum systems are entanglement. So suppose we have two qubits or quantum bits and they are in superposition, and we can create a entangled state out of those two qubits, and then we can say that these two qubits are entangled if they are correlated, means their measurement outcomes are correlated. And we cannot define the single qubit independently, means they both are entangled or they both are correlated, so we cannot define them independently. And this measurement outcomes is correlated irrespective of the distance between those two qubits. So those two qubits can be on different planet as well. When you measure one of them, you will get the correlated output on the other qubit as well. So see here, this kind of state 1 by square root of 20011 is called a Bell state or an entangled state, because it cannot be defined as a product of two quantum bits A and B. What it means is that you cannot break this two qubit system into two separate qubit systems. So this is the essential condition for an entangled state. And if these states are, we can write like this: phi 1 cross phi 2, means if we can describe this combined state into two phi 1 and phi 2 qubits, then we say that this state phi is separable, means we can write it as a product of two quantum state phi 1 and phi 2. Then these states are separable or not entangled. So for entangled to happen, this cannot be written as an independent product of two qubits. So whenever they are defined in respect of other. So we can define them in respect of one another, not independent. So this quantum entanglement property is exhibited by these objects on spatially separated distance, and the distance can be anything. It can be the two entangled states can be on different planets. Still, they will exhibit this correlation on their measurement outcomes. And it can be used in quantum communication, particularly in quantum communication for quantum key distribution, satellite communication, and in computation also. And this has been shown with different particles like photon, neutrons, neutrinos, electrons, and even small diamonds. So this quantum entanglement has been established in lab as well as in field scenario also. So let's understand that how we can create this kind of entanglement pair of photons. So this with this SPDC process, we can create entangled pair of photons in which either both the photons will have horizontally polarized, or both of them will have vertical polarization. So this kind so what happens in this SPDC is basically you throw some light and you emit two photons with same polarization, either this, or they will be having horizontally polarized photons. So we call this as a vertical polarized, we call it as a horizontal polarized photon, and we can denote this H as a 0 bit and V as 1. So what we are trying to say here is that this kind of entangled pair we can create with this kind of process. So that is not our concern that how we get it. We are having it with different processes. One is one of the majorly used process, that is called the spontaneous parametric down conversion process, wherein with a high energy photon we are able to create two lower energy photons, in which the property is that both the photons has same polarization, maybe vertical or horizontal, we do not know, but both will have same polarization on measurement. If we measure one of the polarization of the photon, then we will have same vertical or horizontal polarized photon, and we can encode our bit information like 1 and 0 in this polarization, vertical and horizontal. So maybe we can write like this: it's 1 by square root of 00 plus 1 1. So what we are trying to say here is that if we have these kind of entangled pair of photons, then whenever one of these photon is measured, so you do not know whether the polarization will be horizontal or vertical. But suppose these two photons are there, let's call it P1, P2. So if you measure one of the photons, and if you get first photon as on measurement as is horizontally polarized, then you are sure that the other photon will also be having the horizontally polarization. Maybe the photon can be on different planets. So suppose this P1 and P2 are there. So we entangle them, we create this kind of state, and we are putting this P1 and P2 photon on different planets. So what we are trying to say here is on measurement, we do not know whether the polarization will be horizontal or vertical. But if we measure one of them, and suppose we get horizontal polarization on the first photon, then instantaneously the photon 2 will also have the same polarization horizontal. So before measurement of this, we do not know whether it is HH or VV, but on one of its measurement, we are sure about the other one. And if we try to see in terms of probabilities of these states, then this 1 by square root 2 is nothing but the coefficient or amplitude of these states HH and VV. So this is amplitude, and if you want to have the probability of having HH on measurement, then it will be 1 by root 2 square. So that is 1 by 2, 50%. Same for VV also. So getting HH or VV is 50-50 probability. But once you measure one of them, you are sure about the other one. So measuring horizontal or vertical on first photon is 50-50. But once we measure one of them, we are sure about 100% that the other will be also same. So this property is exhibited by photons on a large distance. Okay, and this distance can be anything, and it has been demonstrated in lab environment and through satellite based system also. So how we can create this kind of entangled state? The question is this. So as we have seen that as we have seen already that with this process physically we can create this kind of photons, and in a quantum computer also we can create this kind of pair using special quantum circuits. So suppose if we have this two qubit system X and Y are there, and if we apply the Hadamard gate on the first qubit, and then we apply the control node on the first to second qubit, then at the end we will have the Ball-State pair. So if we put the typical values of X and Y, then we will be seeing this thing. So let's, if we start this first and second qubit, let's call them as a Q1, Q2. And what we are trying to say here is that we are applying Hadamard gate, and then we are applying control node gate. And at the end, we are having this beta 00, that is our Ball-State we are obtaining. So if some of you do not know what a Hadamard gate does, then it is basically when we apply the Hadamard gate on a 0 state, it creates the superposition of 0 plus 1 state. And in this, both 0 and 1 are equal probable. So this kind of state it creates when it is applied on 0 state. So and so here it will be like this. And what this C0 gate does? So C0 is control node gate. So what it does is when you apply C0 gate from qubit 1 to qubit 2. So we call this as a first as a control qubit and second as a target qubit. So what happens is when you apply control qubit Q1 is 1, then this qubit 2 will be flipped. So how it is done is with this kind of expression we can write like this: Q1 XOR Q2. So whenever this Q1 is 1, this will flip the Q2. So understand with this thing, whenever this Q1 is 1, it will be flipping the Q2. So with this operator not we call as, so whenever the control qubit is 1, it will change the target qubit, but the control will remain same. So this qubit 1 will remain same, only the qubit 2 will be changed. So basically qubit 2 is our target that is flipped when control qubit Q1 is 1. So these two gates, when we apply in this configuration, we get beta 00. So we can see how these states are being evolving with this gate operations in the next slides. So initially what we are having is both the qubits are 0 0. So see, this is your first qubit, this is your second qubit. So on the first qubit q1 and q2, what we are doing is we are applying the Hadamard gate. So as we have already told that Hadamard creates, when applied on 0, it creates 0 plus 1 by root 2, and second qubit will remain same because on second qubit we are doing nothing. So we are initially here both 0 0. When we apply the Hadamard gate, so the state will be like this: 0 plus 1 product 0. When we do that product, then we have 0 0 plus 1 0. So this is our state psi1 at this position. Now what we are doing is on this psi1 we are applying control node gate. So what this control node will do is, control node, when the q1 is 1, it will flip the target qubit q2. So see here, in this control q1 is 0, so it will not change the target, so it will be 0 0 only. But see here, this is control qubit q1, that is 1, then it will flip the target qubit, so it will become 1. So the state is like 0 0 and 1 1. So we can write like this, and this is our Bell state, and we call it as a Bell state 0 0. Why 0 0? Because in the initial we are initializing these two qubits with 0 0, so we call it as beta 0 0. And this way, with simple gate operations, we can create Bell state, and which shows the entanglement property. Okay, so in entanglement, what I have already told, that if you create this kind of state, and then you can take this qubit q1 at some place and q2 at other place, and when you measure them, q1 and q2, they are correlated. Either they both of will be 0 0 output, or both of will be having 1 1. Okay, and once you measure one of them, you are sure about the other as well. That once I measure first qubit as 0, then I am sure that second qubit will also be 0. And once if I measure 1, then I am sure about the other qubit that will be also 1. So here the correlation is same kind of thing. If one is 0, the other will be 0. Okay, but we can create other kind of Bell state as well. Suppose if we initialize these two qubits with 1 1 state, and we apply the Hadamard and then control node, then we get this kind of Bell state. What is the property of this kind of Bell state? So see here, q1 q2, q1 q2. So see here, if the first qubit is measured 0, then second qubit will be 1. If the first qubit is measured 1, then second qubit will be 0. So basically they are anti-correlated. Still the correlation is there, and that is anti-correlation. What it is? They are opposite of each other. So whenever you measure one of the qubit, suppose if you get x, then on other qubit it will be x prime or x dash. So they are opposite of each other. How we can create? Just we are initializing these two qubits with 1 1, and then applying the Hadamard gate. So if you remember, Hadamard gate on one state create 0 minus 1 by root 2. So here minus sign is there, that is to represent the phase value. And now we are applying again the control node gate, so we get this kind of state, and we call it as a beta 1 1. So here the outcome is this 0 1 and 1 0, means the states are anti-correlated. So this kind of Bell state also we can create and can use. So this way we can create 4 kind of Bell states depending upon the input x and y. So suppose your x and y is 0 0, then this is the first state you can create. Suppose the input x and y is 0 1, then we will have this kind of state. Likewise, this 4 states, Bell states we can have. And the property of this first and the last, first and the third one is that they are similarly correlated. If one of the qubit is 0, then other will be also 0. Means in these two beta 0 0 and beta 1 0, they are same output will on both the qubits, wherever the distance between these two qubits. But in case of this beta 0 1 and beta 1 1, we are getting the correlation opposite of each other. So when you measure one of the qubits, if you get 0, then other will be 1. If you measure one of them is 1, then other will be 0. So they are anti-correlated. But still, both of all of them exhibit the correlation, and these Bell states are called after the name of scientist John Bell, and these exhibit maximum entanglement. Can we create on a quantum computer or a quantum simulator? So we will see that. Before seeing that, we can have 3-qubit quantum state also. 3-qubit quantum state which can show the entanglement. So in that, what we do is, okay, so let's first understand this Bell state on the IBM composer, then we will see the GHZ state. So let me share my screen. Yeah. So there is this website called IBM Quantum website is there. If you Google that, then you will be able to log in into that. So if you search with the key term composer or IBM Quantum, then you will have this kind of website, and you can log in with your email ID, or you can create your account, and you can come to this composer platform. So what does this IBM composer platform provides is that graphically you can create quantum circuit, or you can implement your quantum algorithm or application as well. But in our case, we just want to implement the Bell state quantum circuit. So what we can do is, just we simply, what it did is that we initialize both the qubits Q0 and Q1 as 0 0. So this kind of gate you just simply drag and drop, and you can create. So I'm just deleting it. Okay. My session has been out, so let me relog in again. So far any question is there? Let me check into that. Any question is there?
No questions are there.
Okay. So you can log in into this IBM Composer. So I have logged in into my this thing with my Gmail ID, and when you will have this kind of interface. So suppose if we want to create this kind of Bell state, so which we have seen here. So see, remember, we need 2 qubits initialized with 0 0, and then we apply Hadamard gate and then control, and then we will be measuring. The same thing I am trying to implement with quantum circuit on IBM Composer platform. So we are initializing both the qubits by 0 0. So we have taken 2 qubits. Additional qubits we are deleting, because our circuit require only how much qubits? Only 2 qubits. And this double line denotes the classical bits. So we require only 2 classical bits to measure our outcome. So we have taken 2 classical bits. Then the first step is that Hadamard gate we need to apply on the first qubit. Okay, and then control knot on first to second qubit that we have placed, and then we will be measuring the outcomes. So see here, the just I want to show them how this circuit is progressing. So in the beginning, if you see, both the qubits are 0 0, so the state will be like this, 0 0. So see the state vector here, the amplitude of state 0 0 is 1. There is no other state in superposition there. Then we apply Hadamard gate. So after application of Hadamard gate on the first qubit, so the first qubit here is, if you see these amplitudes here, computational basis. So the first qubit from this is our LSB, and that is both 0 and 1. See here, this qubit is 0 here and qubit is 1 here. While the second qubit, that is this one, Q1, is 0 only, because we have not changed it. So what we are having here is, we are having state 0 0 and 0 1 in superposition. Now when we apply the control NOT gate, so see, when we apply the control NOT gate, what we are having is 0 0 and 1 1 state, and you see the amplitude, that is 0.707. That is nothing but 1 by square root 2. See here, 1 by square root is there on the coefficient or the amplitude of these states 0 0 and 1 1. So see here, 1 by square root 2 should be the amplitude. So see here, we are having the same amplitude, 0.707 and 0.707. And if we want to calculate the probability, then we need to just mod square this amplitude. So if we square this amplitude 1 by square root 2, then we get 1 by 2 probability. So see here, that is 50% of getting 1 1 and 50% of getting 0 0. Okay, so those probabilities, like uh, on measurement we will have either 0 0 or 1 1, but we do not know before the actually measuring. And if we measure one of the qubit as 0, then we are sure that the other qubit will be also 0. And if we, okay, so yeah, and if we put the measurement thing here and measurement gate here, so what it will do is it will measure those outputs in the these two classical bits. So suppose in this iteration it observed as 0 0, so it can observe anything of 0 0 or 1 1. So if we run this thing 1024 times, so here what we are having is, if we run this circuit 1000 times, then what we are expecting is that 50% time we should get 0 0, 50% time we should get 1 1. So see here, almost 49.6 we are getting this, and 50.39 we are getting 1 1. So there is almost 50-50 probability. Okay, and when we increase the number of circuit iteration, instead of 1024 shots, if you run the circuit 10,000 times, then this thing will be approximately 50-50 only. Here it is slightly more for 1 1 state, and it is slightly less for 0 0 state. But when we increase the shots, then we will get the almost same probability for 0 0 and 1 1 state. Similarly, if you want to create the other states, then you just simply need to put the X gate. So it will become 1. So this is our X gate. So we put it here. Okay. So now what we are having is, we are having 0 1 state and 1 0 state. And these two states are anti-correlated. Means if one qubit, if we measure 1 0, what it means is that first qubit is 1, then second qubit will be 0. And here also opposite relation is there. So in this case they are anti-correlated. So here what we have done is that with this thing we can create this kind of different entangled state on this platform that we call as a IBM composer. And it is very simple here, and we are seeing that results also according to the distribution which we see in the slides. It is a very easy or starting way for start doing quantum programming. If you do not know the quantum programming, then you can start with this kind of quantum circuit creation here, and you can experiment with it. Here also, if you have the credits, then you can run those things on actual quantum computers. Okay, so with this region you can select the computers and you can run your applications. For that you require some credits, or you need to pay to IBM. Some credit are given free, but when you have money, then you can buy computing time and you can run on different IBM computers available online. So here these things are being simulated. So simulated results we are getting, and we can run the same thing on actual quantum computer as well. So before running on quantum computer, we do these things locally, and this is a graphical way for beginners. And there is another elegant way using Qiskit framework, wherein we can use Python programming to do the large scale quantum applications or algorithm implementation. So far this thing is clear, that how we can create this kind of Bell states using composer. Participants, or any questions is there?
No questions.
Okay, so then, so this was we have done with composer. Now we move to, okay, yeah. So Bell state we have seen, and using this we can do many things. We can do quantum teleportation, which we will see in subsequent slide today. Yeah. So in quantum teleportation section, what we will be doing is, first we will understand what this quantum teleportation is, what actually it does, and then we will see the circuit implementation, and we will try to derive with an example how these states are being transferred. So before starting this thing, what we actually do in quantum teleportation is we just basically try to transfer this state size information, alpha times 0 plus beta times 1, this information or the state we want to teleport from Alice to Bob. This qubit itself is not going. This qubit can be realized by suppose a photon. This photon is not going there, but there is an equivalent state with having this same coefficients alpha and beta will be created at Bob's side. Initially, Bob does not know what is alpha beta, and even Alice does not need to know what is alpha beta. Alice has some arbitrary state psi, and its coefficients are alpha beta, and we want to create the similar or same kind of state psi at the Bob side. So, to and Bob can be at any distance. They can be on different planet as well. So distance is not a restricting criteria. Distance can be anything. So understand one thing, that we are just transferring the quantum state of this state psi. We are not physically uh, uh, teleporting or transferring this photon, which is shown here in the red color. We are not sending this photon to Bob. We are just trying to recreate this kind of state which has alpha and beta coefficient at Bob's side. So for that, what we require is we require an entangled pair, which we have shown in the previous slides, and what we call that is as beta 00. So we can create this kind of entangled state beta 00, in which getting 00 and 11 probability is 50-50. So suppose if we have this kind of Bell state with us, and there are two qubits. Suppose this is your, let's call it as a Q2 and Q3, Q2 and Q3. Then what we are trying to say here is that in lab environment, we have created this kind of Bell states with Q2 and Q3 qubits. And what we are saying is that Q2 we are giving it to Alice, and Q3 we are giving to Bob. So what we are doing is, with entangled pair of photons, we have created it, suppose, or any other way we can create this kind of state. And what we are doing is we are giving this first quantum particle, that is we are calling as Q2, to Alice, and Q3 to Bob. So Q2 is here and Q3 is here. And our goal is that we want to transfer the state of this psi from Alice to Bob. Okay, so what basically we have is, we have a qubit 1, that is we are calling as a psi state, and then we have an entangled pair of qubits Q2 and Q3, in which also what we are saying is that this qubit 2 is with Alice and this qubit 3 is with Bob. At the end of this quantum teleportation protocol, what we desired is, at the end this psi should be with Bob, or the qubit 3 should have psi. Okay, so we will see that how we can implement that. So as I just now explained, that Alice initially has this psi state, and one part of this entangled qubit that we are calling as a Q2, Q2, Q3, Q2, Q3. So Q3 is with Bob. So what in this protocol happens is that Alice performs some operation on her qubits. So this is, her qubit is Q1 and Q2. She performs some operation on these two qubits and then measure them. On measurements, she will have two classical bits of information. Let's call it M1 and M2 bits. Then she will send the measurement outcomes to Bob with classical channel. So what she will be doing is, she will be telling that I measured two bits M1 and M2, and it will tell to the Bob. Now what Bob will be doing is, Bob will apply this X and Z gate operations on his qubit Q3. Depending upon the values of Alice outcomes, he will apply some X and Z gate operators on his qubit, and on measurement, and at the end of this appropriate operations, Bob will be having psi. At the end, Bob will have the psi which was with initially Alice. So any question is there, participants? You can unmute and tell. If in understanding this thing there is a question, then you can.
Participants cannot unmute, but there is one question which asks, what if the Eve measures the Q3 in the entangled state Ket1?
No, Q3, just see here, Q3, qubit Q3 is with Bob, and Bob is not measuring initially. Initially, only the qubit 1 and qubit 2, which are with Alice, and she is measuring. And she is telling what she measured. 2 bits, like ones. She shares those 2 bits of information to Bob on classical channel. Then Bob will apply some quantum operation on his qubit 3. On applying those operations, then he will measure. Then he will observe that he is having the same state psi with him. So Bob will be doing the measurement at the end. Does it answer my question? Your question? And we are not sending this photon physically there. We are just teleporting the state, and then the state is with nothing but alpha and beta. This coefficient depict the state. So at the end, Bob will have similar kind of state which has alpha times 0 plus beta times 1.
There is one more follow-up question.
Yeah.
When Alice measures Q2, Q3 gets automatically affected as Q2 and Q3 are entangled. Then how can Bob have the qubit Q3 intact?
No. So what we are saying is that Alice is measuring the part Q2. Bob will be having the Q3 with him, and if we do not do anything on this qubit, and if we measure, suppose Alice measures 0, then Bob will also measure 0 at this point. But what we are doing is, we are not measuring it. We, on this qubit third, we are applying some operations, quantum gates, X and Z gate we are applying. So after application of those gates, it becomes psi. If you do not apply anything on this qubit 3 and you simply measure, then it will also have the same thing which Alice observed. So what we are doing is, before Bob's measurement, we are applying some operations, X and Z gate, on this qubit 3, and then we are measuring. So on measurement, we are observing that it is not a Q3, it has become psi due to these 2 operations. Maybe with the example and the quantum circuit, it will be more clear. So this is typical quantum teleportation protocol circuit, in which, as I explained, this is your Q1, this is your Q2, and this is your Q3. So you create bell pair beta 00 state, and you given this Q2 to Alice. So Alice is having what? Q1 and Q2, and Bob is having what? Q3. Now what Alice is doing is, so if you see here, this part, so that we have denoted as a Q1, Q2, and Q3. So what Alice is doing is, suppose Alice is having some state psi, she is applying a control knot operation from the first qubit to second qubit. So because this qubit 1 and qubit 2 are in possession of Alice, and while this qubit 3, which is part of this bell pair, is with Bob. This part is with Bob. Okay. Now what Alice is doing is, she is applying this operations control NOT gate from first qubit to second qubit, and then applying the Hadamard gate on the first qubit, and then she is measuring her 2 qubits. So this first and second qubits are with Alice. She can apply any operation she desires. She can measure anytime she wants. She measures. She observes M1 and M2 classical 2 bits. This M1 and M2 are what? Classical bits. So this M1 and M2, this can be 00 or 01 or 10 or 11. Okay, because these things are probabilistic. So it depends upon what is psi. So depending upon the psi value, it may be observing 00, 01, 10 or 11. So whatever it observed, suppose it observed M1 and M2 variables. two bits she observed or she measures. Then these two lines denote the classical bits. Single line is basically we are working in quantum domain, okay, on qubits. Two lines means we are working on classical bits, and those are M1 and M2. What she is doing is Alice is sending these two bits of information M1 and M2 to Bob, and Bob is distance away, okay, but Bob has this Q3 with him. Okay, this is Q3 which is with him. Okay, so what will happen is that depending upon the value of M1 and M2, Bob will apply X and Z gate on his qubit Q3. So Q3 is intact with him. If this point you measure, then then Bob will be also having the same thing which Q2 was there. So see here, this Q2 has been modified here. Okay, so it is no longer that state which was there originally. So Q2 and Q3 were combinedly there, 0 0 plus 1 1. Now we have modified Q2, and we are not measuring here. If we had measured at this point, then maybe we are having a similar kind of output here. But what we are doing is, depending upon the value of this M1 and M2, we are applying X and Z gate on the third part of the qubit Q3, that is with Bob. And what we are claiming is, at this point, Bob is having state psi with him. Sorry, getting this question and understanding at high level this protocol?
There are few
Okay.
questions.
Yeah, please.
So while teleporting, will they get the same qubits?
No. Sorry, what is the question?
While teleporting, will they get the same qubits? एक बार ऊपर scroll.
Why teleporting?
So while teleporting, will they get the same qubits? Means Alice and Bob will get the same qubit.
No. You understand one thing. At the end of this protocol, initially at time t1, if you see here, let's call it time t1. At time t1, Alice is doing all these things. At time t2, Bob is doing this thing. At time t1, in the beginning, Psi was with Alice. And even Alice was not knowing what is this alpha and beta. Alice was knowing that I have some state psi. Whatever this alpha, beta, whatever value it takes, she does not care about that thing. She has some arbitrary state psi, which has some coefficient alpha and beta. She does this gate operation and measurement, and she gets this two-bit output. Now what we want to do is, we want to recreate this psi at Bob's side. So once you measure the first qubit here, this psi is lost. Psi is no more here. Okay, psi has been measured. But what happens is, with this entanglement and this C0 gate, we have transferred some information here. And since this Q2 and Q3 are entangled, so this information is transferred to this Q3 also. Information about psi has been communicated to Q2 with these gates. And then, since these two qubits are entangled, so this to Q3. And if we apply this X and Z gate, then we can have exact psi here. And this psi is nothing but alpha times 0 plus beta times 1. So physically this qubit has been measured here, and this photon has been lost. What we have here is that this qubit 3, which can be a photon, is having similar or same alpha and beta coefficients. Same state. Because this state is nothing but this alpha and beta. So at the end, we are saying that at time t2, if Bob does these operations, then he will have the psi state with him.
Okay,
is it clear?
So next question is this under control of Alice only or Bob? I think he's talking about quantum teleportation, whether it's in the control of Alice or Bob.
Our purpose is like that Alice want to send this psi to Bob. So if we do these things in this fashion, at the end, Bob will have psi. So both are in control. So basically Alice doing this operation, if she does not perform this operation properly, if she does not send this classical bits 0 0 0 whatever she observed, and if she does not transfer these values properly, then Bob cannot apply X and Z properly. So both of them are in charge, and combined goal of Alice and Bob, with the help of this entangled qubit B00, they want to transfer the state of this state psi from Alice to Bob, and they are distant away. So both of them are working in collaboration to get this thing established or happen.
Okay. Next question is, does this mean that X and Z gate does not cause entanglement?
No, for entanglement, this control node gate is the thing. If you remember from the previous slides, with this Hadamard and control node, we are able to create entangled state. So control node gate is the key gate which creates entanglement.
Next
First, we
question.
want to establish. Yeah, please.
No, you were saying something.
Yeah. So what I was saying is that uh, control node gate is used for creating entanglement. Here just what we are doing is X and Z, because at this qubit Q3 we have psi in some misarranged format. This alpha and beta are swapped and this sign is not proper. So with this X and Z gate, we are swapping this alpha and beta, and we are just changing the sign so that we get exact alpha times 0 plus beta times 1 at the end here. So this X and Z gate are applied so that we can get exactly psi here in the third qubit. Let's
Okay.
understand with this. Yeah, we can take some questions later on also. Yeah, any questions, sir, there?
Yeah,
Or
there are few more.
yeah,
So,
please. Okay, then.
should sharing the type of bell pair required here?
Yes. So what happens is that in the beginning, first we should have an entangled pair beta 00 with Q3 and Q2 and Q3, and at this point these two are at the site of Alice only. So what we want is that in the beginning, suppose some third party, or maybe Alice or Bob, uh, third party Alice or Bob, whoever is having this pair beta 00, what they will do is they will send this Q2 to Alice and Q3 to Bob. So suppose if Alice is creating this pair, then Alice will keep Q2 with herself and will send this Q3 to Bob. So initially this pair is created, and one part of it is given to Alice and other part is to Bob. So maybe third party can also do this thing, or maybe Alice or maybe Bob. So anyone can do this thing. What we want is that at the end, Alice should have Q2, Bob should have Q3. Any other questions?
There is one question related to gate, which is saying X
Yeah.
superscript M2 and Z
Yeah.
superscript M1. What is the meaning of representing in this way? So the symbol which you have
Yeah.
written on the gates, what does that mean?
Yeah. Yeah. So M1 and M2 are classical bits. They can take value 0, 0, 0, 0, 1, 1, 0, or 1, 1. So suppose this M2 is 0, M2 is 0, suppose, then X power 0, what we are saying is identity. So means we will be not applying any gate. Identity means we are not applying anything. Suppose this M1 is 1, then it will be basically Z gate. So we'll be applying Z gate. So we will be applying Z operation on the third qubit. And if you want to understand what this gate does is, then I can write here. Yes. So X gate, if you apply on 0 qubit, then it makes it to 1. X gate, when you apply on 1 qubit, 1 state, it will make them 0. Similarly, if you apply Z operation on 0 state, Z, so it will remain 0 only. And if you apply Z on 1 state, then it will change the sign. So these are X and Z gates. So what they do is, X just flip the bits 1 to 0 and 0 to 1. Z on apply on 0 state, it will remain same, but when state is 1, it change the sign. So if you apply this kind of gates on general state psi, so general state psi, how we can write? We can write like this: alpha times 0 plus beta times 1. So suppose if I apply X gate on this psi state, X gate on psi state. So what it will become? It will become 1, 0 will become 1, and it will become 0. If you apply X gate on psi, and if you apply Z gate on psi, then you know that 0 will remain same, but it will become minus beta, because 1 becomes minus 1. So this will be minus beta. So this is basically the working of these two gates, X and Z gate. One gate just X gate just flips, and Z gate change the sign of one state. Any other question is there?
There is one more question. What is the purpose of using Hadamard gate?
Hadamard is generally used to create superposition. So if you remember from previous slides, Hadamard, if you apply on a 0 state, then you get 0 plus 1 by root 2. And if you apply on this kind of state, 1 state, then you get 0 minus 1 by root 2. So just to create superposition, it is used. When we derive the stages psi 0, psi 1, psi 2, psi 3, and at the end we will show that psi 4 is nothing but psi only, then you will see the effect of these different gates, gate and Z gate and Hadamard gate. So maybe after a break of 5 minutes we can start, and we can see the derivation. If any other question is there till now, then I can answer right now.
No questions. You may continue.
Okay, so we should break for a while now, or
Yes, we can break for 5 minutes.
start at
We
3?
can take a break for 5
And we can
minutes and
start at 3.
Yes.
Okay, we can start at 3 o'clock.
Yeah. Thank you.
Okay. Okay.